All right, here we are for your first video for Math 26. You'll find that in this class, we actually start at chapter 2, which seems odd. Normally you start in chapter 1, but we are not doing that. We are starting in chapter 2. The first half of chapter 2 is going to be review from algebra. The first couple of sections, there are 6 sections total. And then the second half of chapter 2 is going to be where you start talking about those foundations of calculus. In 2.4, we're going to be talking about limits. That's a pretty big section, and a lot of what we do in these early sections, 2.1, 2.2, 2.3, that's going to be used again as we apply it to calculus topics. So the actual new stuff for you will be in 2.4, 2.5, 2.6, and basically everything after that until we hit chapter 5, and you'll start seeing some review again. But if you just had college algebra like last semester, well, you can sit back a little bit, take the notes, definitely watch the whole video, make sure you're on the same page as everyone else, because you definitely need to have a good solid foundation of this review material before you get into your calculus material. But definitely make sure that when we hit 2.4, you're understanding this is where we're hitting some new material, and you need to be on your A game, making sure that we're on top of these notes. So 2.1 is all about functions and their graphs. And yes, in your prerequisite, whatever that was, whether it was college algebra at ECC, or maybe you took algebra 2 in high school or something like that, you should have seen these concepts before. Now, I always end up with students who tell me, I haven't had algebra in 10 years. Make sure that you're really paying very close attention to these foundations in the first couple of sections, because if you haven't had algebra in 10 years, you're really going to have to make sure that you can keep up with the algebra. I always tell my calc students, it's not the calc part itself that's hard, it's the algebra. It's being able to take these calc concepts and put algebra in them and, be able to come up with the correct solution. And have a good understanding of what's happening. So if your algebra foundation is weak, it's really important that you get that together as soon as possible. All right, without further ado, functions and their graphs. A function is a rule that assigns to each element of one set or domain exactly one element of another set in the range. If you are like, okay, that makes no sense, fine. We're going to look at some examples of this and you're going to see it in action. And I think once you see it, you're like, okay, got it. Another definition of a function is a set of ordered pairs for which no first x coordinate is repeated. So if it's been forever since you've had algebra, I'm going to remind you right now that when you're looking at an ordered pair, you're looking at this set of coordinates that lies on the coordinate plane. First coordinate is the x value, the second coordinate is the y value. So they're always in these parentheses. So if it's been a really long time for you, I'll remind you which one's which. So your domain is the set of inputs, which is typically the set of all x's. And this is your input variable. So you're putting things into the domain and then you're getting an output, which is the values that are popping out in the range. And those are the y values. So y is dependent on x. X is the independent variable. So as we're looking, I'm going to give you an example here of a relation. And this particular relation happens to have 4 ordered pairs in it. And I will ask you then, is this a function? If it is, we can talk about the domain and the range. So what we're looking for here is we're looking for whether or not we have values that repeat. And actually, we can still, sorry, I should specify, we can still find the domain and range, even if it's not a function, or whether it's a function or not, we'll be able to find the domain and range. But first, we need to be able to determine whether it's a function. So the easiest way to do this when you're looking at a set of ordered pairs is to check and see if any of the x values repeat. If any of the x values repeat, then it's not a function, assuming their y values are different. So for instance, I have -3, 1, 5, and 1 for the x values, but the 1 appears twice in the second and fourth ordered pairs. So these x values repeat. Because they repeat, we could say that this is not a function. It is a relation, but it's not a function. Now, if the y values were to repeat, well, that's okay. You can still have a function where the y values repeat. You just can't have a function where the x values are repeating because it's not a function. We'll talk about the domain and range in a second, but I also want to remind you of something because this is review. Another thing you could do to determine whether your relation is a function is you could set this up on a coordinate grid and you could graph these 4 points. So for instance, this point at -3, 8, and we should probably do some review of plotting points anyway, if it's been a while for you. -3 would be left on the x-axis, and then 8 would be up on the y-axis. 1, 2, 3, 4, 5, 6, 7, 8. That coordinate would be right about there. And then the coordinate at 1, -3, would be right here. Now at 5, 8, you'd be up there. And then at 1, 1, you'd be at 1, 1 right here. So when you're asking yourself, do I have a function? Another way that you could look at that is to ask yourself, if you could drop a vertical line through your plotted points, would you ever hit one y value more than once? So if I was to drop a vertical line here through x equals 1, notice that you would hit 2 different points. So right there, that tells you it's not a function. If it's been a while, it's called the vertical line test. We will talk about that next. But because students tend to always remember the vertical line test so well, it's just one of the big takeaways from algebra for some reason. I just wanted to make sure to mention that with this particular set of values. And notice that even though these y values of 8 repeated, that would technically violate a horizontal line test, which we wouldn't even worry about in this case. We're not really going to talk about the horizontal line test in this class. It's not for determining whether you have a function, but it is a thing for determining other things that we're not going to talk about. So notice that these 2 values don't cause an issue with your vertical line. Once you've determined whether your relation is a function or is not a function, make your conclusion, and you can write down the domain and the range of the relation. The domain is the x values. Now, normally when you list the domain, you list the values in order from least to greatest, and you don't repeat any values. So even though we have 1 here twice, we're only going to write it 1 time when we write the domain. You're not supposed to repeat it a second time. So I'm going to pick out the smallest of the x values, which is actually -3, and start there. And when I write a domain and a range, what I'm writing is a set of values. To write a set of values, I'm going to include these braces for set notation. So I'm going to start with the smallest x value that appears, which is -3. The next one is +1. I have it twice, but I'm only going to write it once. And then the next x value is 5. So those are the values in the domain of the function. The values in the range would be the y values. So I'm going to be looking at the second coordinates here. I also have -3 as my smallest value in the range. So I'm going to do something similar here. I'm going to use set notation. I'm going to start with the smallest value in the range, and then I'm going to go up to the next largest value, which is +1. And then the next one after that would be 8. Okay, so let's see. -3, +1, and 8. So that's how we talk about domain and range, and that's how we determine whether or not we have a function when given a set of ordered pairs. The next thing we're going to do is talk about that vertical line test one more time. So the way the vertical line test works is if the vertical line intersects the curve more than once, well, if no vertical line intersects the curve more than once, then the curve represents the graph of a function. So you're going to just try to see if you can find a place where you could drop a vertical line through the graph and hit the graph in more than one spot. Now, by the way, these dashed lines right here, in case you don't remember, the vertical ones are called vertical asymptotes. Those don't actually exist on the function. They're just boundary lines that tell you how far your graph can or can't go. And then there's another horizontal asymptote that's guiding the x values and kind of saying what their boundary is. But you know, you could pick any place on this graph and notice that you would only be able to hit the graph in one spot when you drop the vertical line. So here I would hit the graph at that point. If I drop the vertical line right here, I would only hit that one point on the graph. Sorry, my vertical line game is a little off today. But you're not actually going to be able to find a place where you could hit the graph in more than one spot. Even if I tried to drop a vertical line somewhere here in between these vertical asymptotes, I'm only going to hit the graph at exactly one point. So what you're looking for with the vertical line test is like what might happen, like if I had something graphed maybe above this or something below here where I would actually hit the graph twice. There's no way that that's going to happen here. You're only going to hit the graph once. So we would say that yes, it is a function. You're never going to intersect that graph more than one time. Now, again, we kind of talked about that with this example. You would have hit that graph 2 times when you drop the vertical line through, and we already said it's not a function. So it's really helpful to be able to look at these in more than one way. It's not like you have to do it one particular way. But when you're given a graph, the vertical line test is going to be the easiest way of doing that because we weren't given any function or any points on the graph. All right, so it's a function, and we'll talk about the domain values. So the domain is just the values that x can possibly take on. The way that I usually look at the domain is because I'm looking at the x values. I'm going to go from left to right on the graph and just see what values are covered. So I know if I start all the way down here where x heads up from negative infinity, I'm covering all the values. This graph exists for all the values of x up until I get to this boundary line where I have this vertical asymptote at -1. So I usually will abbreviate vertical asymptote, but we'll say that that occurs at x equals -1. But we also have another vertical asymptote here at x equals +1. Vertical asymptote at x equals +1. Now the asymptotes represent places where the graph can't possibly exist. So I know that as long as I choose any value of x from negative infinity all the way up to this vertical asymptote, I'll be able to get a value on the graph. I just can't possibly have anything graphed on this dashed line. It's like a big no-no. So my domain is going to start, I'm using interval notation here. Interval notation. Your homework will ask you to use interval notation, so we have to know what it is. We're starting with values of x that can go all the way down to negative infinity, and we have to stop up here at -1. Now, we can't actually be equal to -1 because we have that boundary line there. So what we're going to do is we're going to set up a parenthesis there that says that we can get as close as we can to -1 without actually being -1. So like -1.1, -1.01, -1.001. We can get so close, but we can't get to -1. And we'll talk about that concept a little bit more when we start talking about limits, but that's sort of that idea. We can get infinitesimally close to -1, but we can't actually exist at -1. But what happens then is we can pick these values back up again because you'll notice the graph exists between -1 and +1. You've got this little chunk of the graph. When you pick up another piece of the domain, we connect these with a union symbol. So we're saying, okay, x can exist here, and then we're also going to connect that to the next interval between -1 and +1. Again, we can't equal those values because there's a vertical asymptote there. So we'll just leave it open. If we could be equal to those values, then we would use a square bracket like you learned how to do in algebra. And then we can pick those values up again as we approach to the right of +1. X can take on any value from +1 to positive infinity. Any value is fair game. You'll see that there is something graphed for those values. So really what we're looking out for with the domain, and we'll talk about this a little bit more later on too, is just making sure that we're not including any values where we have these vertical asymptotes. For the range, you're looking at the values that y can possibly take on. Notice that if we do something similar, but instead of going from left to right, I go from bottom to top, we're just looking at values where there's something graphed for y. So if I start at the bottom, I'll notice that I have values that exist starting with, I mean, we're just going to assume this is y heading off to negative infinity. Maybe it would be helpful too if we put some arrows on these so you kind of had a sense that this behavior is going to continue on. They're not just like segments. So whoops, I put the arrow on my vertical line. So this graph is going to come up from negative infinity. It's going to come all the way up to y equals -1. And then once it gets there, it heads back down again. Now notice that you don't actually have anything graphed between y equals -1 and y equals +1. That's just blank space where you don't have anything graphed for your y values. So when we write the range, we're going to say that this range starts at negative infinity because I can take on any y value that goes all the way down to the end of time. It's going to come all the way up to -1. And I can actually equal -1. I do have a point here. If x is 0, y is -1. And since we can actually reach a value there, we can include that in the interval notation with a squared off bracket, not a circular, not a parenthesis. The parenthesis means like we can get close, but we can't touch it. This one we can touch, we can attain that value. And then we're going to pick that interval back up again for values of x that are larger than 1. Sorry, values of y that are larger than 1. Notice, though, that we have this horizontal asymptote at y equals 1 that will not allow us to graph any values of y at or below that in between these values. So we're going to go ahead and say that now our y values pick back up again for values that are greater than 1. So I'm going to start this with an open parenthesis at 1 and then send that all the way off to positive infinity. So remember that the domain is the values x can take on, and the range would be the values that y can take. All right, so that's that. All right, now we're going to use this graph in the example to answer some questions. Oh, I love these. I love these questions. I don't know what it is. Maybe it's because sometimes students aren't the best at being able to read graphs, and just going through questions like this really helps you to get a better understanding of what's happening to the graph of this function and just how to read the notation. By the way, recall that f of x is y. So when I say f of x, I'm really talking about a y value. So when we're looking at this function notation, in this case, I'm talking about f of 0. Well, that means that if I'm talking about f of 0, then x is 0. So if I'm going to use the graph to answer these questions, and I want to know what is f of 0, that means that I want to know what is y when x equals 0. So this means what is y when x equals 0? And a lot of times if you can just interpret these in English words, that's great. That's the whole idea. So what is y when x equals 0? Well, when x equals 0, we're not moving anywhere to the left. We're not moving anywhere to the right. We're sitting right here on the y-axis. And when x equals 0, y is -1. This is something that we kind of talked about already when we put this point here. But when x is 0, we're on the y-axis, and the value of y on the graph is -1. So f of 0 is -1. That is the y value when x equals 0. And then we'll do something similar, this time talking about f of 1. So same question, this time I'm just asking what is y when x is 1? But notice, when x is 1, we have a vertical asymptote. That means we don't actually have any values of y. So we would say that f of 1 is undefined. Does not exist. Either one, you could say. It just means we don't actually have any y values when x equals 1. So we can't find f of 1. For what x is f of x equal to -2? Well, this question is asking you, what is x when y equals -2? So anytime it says f of x equals, think about that as y equals. So if y equals -2, I'm going to look for the x value. Now, notice, however, that you might be looking at this graph and you're like, oh, yeah, y equals -2. I'm going to look on the y-axis right about there. And x looks like it's about a half. Yes, okay, that's fine. You can write that. You can say that x equals a half. But then don't stop there and turn the page and be like, all right, I'm done. What's next? Because notice that you must include any value where that's true. And y equals -2 also on the other side when x is approximately -a half. And do your best to just eyeball this. I know it's hard to get an exact value, but it looks like it's right about at x equals -a half. So you're just trying to figure out what the y value must be and or what the x value must be. And we just said that x is going to be -a half. So if you end up in this situation where you end up with more than one x value for a particular value of y, that's fine. Just make sure you include both. And you don't have anything over here for when y equals -2. Those would be the only two values. If I'm moving from left to right, we can see that. Notice, by the way, that you can have two different values of x for one y, but you can't have two different values of y for one x. So this one was not a function, and this is a function. So just a very minor point to make there regarding this. Okay, next. Another way that we are going to talk about whether our equation represents a function or not is by just looking at the equation. Now, I think it's easier to see it here than here. This is very subtle. What you're going to do here to determine if your equation represents a function is you're going to solve for y. If you get only one value of x back, then it's a function. If y can take, let's see, how do I want to word this? You know what? I'm going to say if you get only one x, if you get only one y for each x, then it's a function. If you obtain only one y for each x, then it's a function. And if you're kind of like, okay, that didn't really clear it up at all for me, well, I'm going to go through these examples, and I think it'll make sense to you after I finish these two examples. If I try to solve this equation for y, I'm going to get y equals, and then I can just say 36 minus x squared. We're just subtracting that x squared term from both sides. Now, I can let x be any number I want, and no matter what it is, I'm only going to get one value of y back. X, I mean, you could even just test some values for this just to get a sense of what would happen. But there's no value of x that could possibly yield two different values of y. There's no value of x that could possibly yield two values for y. There's no way. You can't plug in an x and get two different y's. You're only going to get one value of y for each x. So that means that, yes, you have a function. So a different situation would be something like example 5. In example 5, if you try to solve for y, you could do something similar. You could say y squared equals 36 minus x squared. And if you're thinking like, well, this is not really different, it is different. The reason is, if I wanted to solve for y, remember, if you're trying to isolate a variable that's squared, you need to take the square root of both sides. But what students often forget to do is that when you take the square root of both sides, you have to apply that plus or minus sign. So I would say that y equals plus or minus the square root of 36 minus x squared. Now, this is a very obvious case of when you have an equation that does not represent a function. I can plug in a value of x, and yeah, there are specific values I could find that would only yield one y, but in general, any value of x that I choose will actually pop out two values of y. And if you think about, like, well, let's let x equal 1, well, the square root of 35 and the negative square root of 35 are two different values. So this will yield two different y's for many x values, and it only has to violate that once. So as long as you can find one value of x where you would get two different values for y, that's it. It's not a function. So if you're thinking like, well, yeah, but if I let x be 6, then 36 minus 6 squared is 0, and then y would just be plus or minus 0. Perfect. We only get one value of y. Doesn't matter. We can find other x's where that's not true in most cases. Another way that you could think about this, though, is we know what kind of equations we have here. If you don't remember this one, y equals 36 minus x squared, this is a quadratic equation which is represented by a parabola. Now, I am totally kicking myself here because I have an obscene number of calculators. Oh, wait. I'm trying to get back into my math video mode here. I haven't been into my stuff for a while. Okay, we're good. Never mind, everything's fine. We see this. Oh, and it's showing up because it's daytime. 36 minus x squared is the graph of a parabola. If you haven't done this in a while, you put that in your graphing calculator. It's hard to see because it is a very big parabola, but I know that it's going to go up to 36. So if I adjust my window, I can just adjust that y max over maybe to 40 and just graph it again. And we'll get that parabola show up. This is a function. You're seeing the whole thing here pretty much. I mean, you can see that its behavior is going to go down on the left and down on the right, but you're not going to be able to intersect that parabola with a vertical line in more than one spot. If you dropped vertical lines through here, you're only going to intersect the graph at most one time. So because it's the graph of a parabola, it's just going up here at 36 and heading down. It passes the vertical line test. But in number 5, this is actually the graph of a circle. And if you don't remember that, I don't know, you should have talked about circles in college algebra, but if it's been a while, x squared plus y squared equals r squared, where r is the radius. So this is a circle with radius 6. And the circle can't possibly pass the vertical line test. If the radius is 6, just send it out 6 in all directions. It's not being shifted anywhere to the left or the right. If you were to drop a vertical line through this circle, anywhere you choose, except maybe the endpoint of the diameters here on the absolute extreme left and right, which is, remember when I said, oh, if you picked x equals 6, 36 minus 6 squared gives you y equals 0. Well, that was what happened here, and you'll get the same thing here. So you just get these 0 values. But anyway, I digress. If you drop the vertical line anywhere in the circle, except these two endpoints here on the left and the right, you're going to hit the circle more than once. So this is not a function. And you can think about that in any way you'd like, but just make sure you can justify this. If I put this on a test and asked you, is this a function or not, you can either solve for y and then just, show me the plus or minus, and I'll know, okay, they understand that the plus or minus means it's not a function. Or you could even just graph it and use the vertical line test and show me that. Either way, several ways of doing the same thing. So this would be not a function. And if you will remember correctly, the way that you would actually have to graph this in your calculator would be to graph each piece of this function. So one of the pieces would be 36 minus x squared, and the other piece would be the negative square root of 36 minus x squared. And that's the only way that you have right now of graphing a circle. So if I went back to, let's go to Zoom standard first. So your circle is going to look kind of like an oval because your screen is rectangular and it's scaled out 10 by 10. If you zoom 5, it'll square it out for you, and you'll be able to see the 2 legs of this circle. And if you're like, wait a second, why don't these legs of my circle meet over here? It looks like, it doesn't go all the way to the axis. Well, it can't, because your calculator interprets that as being a vertical segment just because it only has a limited number of pixels, and it can't graph anything that's vertical on your function because then it wouldn't be a function. So it can only do the best that it can do. But this is the square root of 36 minus x squared. Down here is the negative square root of 36 minus x squared, where y has negative values. Anyway, just a little bit of a refresher there from algebra. All right, so that one's not a function. Now we're going to evaluate a piecewise function. I know students hate piecewise functions. Don't hate it, just I love them. Maybe I can transfer my love of the piecewise function to you over this video. They're wonderful and super fun once you get to understand how they work. Okay, right now we're just evaluating it. We're not graphing it. If you want to graph it and then evaluate the values, that's fine, but we're going to graph them here in a couple of minutes. For right now, we're just evaluating. So the idea with the piecewise function, and you should have seen them before, even back in intermediate algebra, is you're being given 2 different definitions for the function. And if you're talking about values of x that are less than or equal to -1, your function follows -1/2 x plus 1. But if your input is greater than -1, then you're going to follow the second definition of the function. So it's going to look like 2 different functions, but it's cut off at this boundary. The boundary is x equals -1. So we're going to use that when we graph these in a couple of minutes. So when you're looking for f of -1, you're trying to determine what is the y value when x equals -1. Now, that's sitting here on your boundary, so you need to figure out which definition it goes with. If I'm talking about a value that can be equal to -1, then I have to use the first definition. The first definition has less than or equal to. For the second definition, we have to be strictly greater than -1, which we don't want to use here because we want to be equal to -1. So in order to find that, we're just going to use the first definition, and I'm going to say that f of -1 is -1/2, and everywhere I see x, I'm going to substitute this value of x, which is -1 plus 1. So you should have done a lot of work with evaluating functions also in your previous algebra class. And then you'll simplify. -1/2 times -1 is +1/2 plus 1, which is 3/2. In general, I would like for you to leave your answers as improper fractions. In this case, because it's terminating, because you can get an exact decimal value, if you wrote this as 1.5, that would be fine. But that's not always the case. Like if it's 1/3, 1/3 does not equal any sort of, it's not a terminating decimal. 1/3 is 0.3 repeating. So that's not okay. You need, if I tell you to leave your answers exact, which will be 99% of the time, it's best to just leave it as an improper fraction. Of course, you could also say this is 1.5. We don't use a lot of mixed numbers in algebra or calculus. The only time we would use mixed numbers might be like in an application problem where maybe it makes more sense to us to talk about quantities that are in either 1.5 or 1.5 versus 3/2. Like if I'm cooking with my son or for baking cookies and I tell him we need 1.5 cups of flour, he's like, all right, got it, 1.5 cups. But if I say we need 3/2 of a cup of flour, I've overcomplicated this, and in a practical sense, that doesn't work. But when we're just working on computations with values, it's a lot easier to work with these improper fractions. No, now I'm gonna try that on him and see if he can figure that out. He's 7, so I don't know, maybe. Right, f of 4. Now this time we're looking at a value that's greater than -1. If we're looking at a value that's greater than -1, then I'm going to follow the second definition. So everywhere I see x, I'm going to substitute 4. You're going to need a little bit more space for this one, so I'm going to kind of start this off to the side a little bit and try to write a little bit smaller. So for f of 4, everywhere I see x, I'm going to substitute 4. So I have 2 times 4 times 4 plus 4 to the -1/2. So there's a little bit of simplifying that we have to do, but that's okay because we need practice. Now, remember that, first of all, well, there are a couple things I want to say here. You can go ahead and multiply the 2 and the 4 to get 8. That's okay. Don't multiply the 4 into these parentheses because this is not really 8, or it is technically 4 plus 4 inside here, but the value is being taken to the -1/2 power. So you cannot distribute a quantity being taken into the first power into a quantity that's taken to the -1/2 power. Can't do that. But I can simplify this, and I can say that this is 8 to the -1/2. Now, if you'll remember, when you have a negative exponent, you can move that value, and you should move that value into a different place in the fraction. So if it's in the numerator, you can move it into the denominator, and then you can make the exponent positive. So we're going to be doing lots of work with negative exponents, and we need to get really comfortable with being able to move those expressions around. Now, this 8 here on the outside is not being taken to the power -1/2. So I'm going to leave it right where it is. So I'm going to leave the 8 here in the numerator, and then 8 to the -1/2 power, I'm going to move it into the denominator and take it to the +1/2 power. Now, the parentheses around this were optional, mostly because I had a negative exponent. It seemed like we kind of needed them to make sure we were being clear about what we were saying. But now we can go ahead and just write it as 8 to the 1/2. Whatever you do, don't cancel the 8s here. Don't do it. You cannot do that. This is not 8. It's 8 to the 1/2 power, which is not 4. It's not 8 divided by 2. Remember that a 1/2 power is a square root. So we are going to rewrite this as 8 over the square root of 8. And if you didn't remember that a 1/2 power was a square root, that's fine, but we're going to be using it a lot in this class, so get comfortable with that. And then you're going to simplify here. If you're like, how would I possibly simplify this? Oh, I should cancel. Don't do that, because remember I said you can't cancel here. We can't cancel between a radical and a value that's not in the radical. But what I can do is I can rewrite the radical using a perfect square factor. So I know that 8 is, yeah, technically it's 1 times 8, but 1 and 8 are not going to help me. 4 is a perfect square. So to simplify radicals, we try to split them. We try to split up that radicand into perfect square factors. So now I can rewrite this as 8 over the square root of 4 times the square root of 2. And now I can start to simplify it a little bit more. The square root of 4 is 2. And the square root of 2 cannot be further simplified. It's going to stay right there. Now you can cancel that 8 from the numerator with a value in the denominator. Not the whole thing, but you know that 8 divided by 2 is 4. Or you could say 2 goes into 2 once, 2 goes into 8 4 times. Either way, 8 over 2 simplifies to 4 over 1. You can rewrite this as 4 over the square root of 2. Now, I'm good with this. You might have learned, though, in a previous class that you need to rationalize the denominator. You don't have to do that in this class, but if you're looking at your homework, for instance, and a denominator is rationalized, I want you to know how to match that up so that you can get your answer to match. So in order to rationalize a denominator, remember that you have to just multiply the numerator and denominator by that radical. So the whole idea is that you don't want to be dividing by a radical. Like I said, this is fine with me as long as it's simplified. I consider a radical in the denominator to be simplified, but in case you need to rationalize, it's going to look like this. The square root of 2 times itself is 2. And then you can simplify that one more time. 4 divided by 2 is 2. So you have twice the square root of 2. So these two are the exact same value. If you're ever not sure, like, wait a second, are these the same? I just don't know. You can always put them in your calculator. 4 divided by the square root of 2 and twice the square root of 2 give you the exact same decimal approximation. So they're the same value. That's a really quick way to just, make sure that your answer makes sense. Either way, it's fine. I'm good with this. If you want to take it farther, you can take it there. Okay. Let's see, what else do we have? Determining domains of functions given their equations. Okay. So this is really important because down the road, we're going to really need to be able to isolate values that our function can't possibly take on. And it's going to make a big difference to us, especially in chapter 4, when we're talking about applications of derivatives. So let's do that now. You should have learned how to do this, by the way, in algebra. Again, everything in here is technically review right now in these first couple sections. So the domain is the set of all valid inputs for x, or the set of all x's that, when plugged into the function, give back a real number for y. Two issues we need to watch out for. One of them would be zeros in the denominator. If your function can possibly take on a denominator that will become 0, then we need to figure out what x value will make your denominator 0. And say, okay, we can't be equal to this value. So we can't have that. Remember that a 0 in the denominator is a case where you're either going to end up with a vertical asymptote or a hole in your graph. So your graph, either way, won't be able to exist at that point. It should be something you talked about in college algebra. Another thing we need to watch out for is a negative radicand with an even root radical or an even index radical. So we're talking about a radical where the index is even and the radicand is negative. So if this looks weird, we're going to look at some examples of this. But remember, I can take a cube root, I can take a fifth root, I can take a seventh root, I can take an odd root of a negative number, and I can still get a value to return for it. But I cannot take like a square root or fourth root of a negative number because I need to be able to find two numbers that multiply together to give me a negative number. And I can't take a negative times a negative and get a negative. I can't take a positive times a positive and get a negative. So if we can't square a value to get there, then we can't take its even root. So now we'll go to the next page. Domains of rational functions. Here's how we're going to find them. We are going to set the denominator equal to 0 and solve for x. The domain is just the values of x such that x cannot be equal to those values you found originally in number 1. Domains of functions with even indexed radicals. If we have a function like this in it, we set whatever expression is under the radical to be greater than or equal to 0, and we solve. So whatever the expression is, we just have to force it to be either equal to 0 or positive. You can take the square root of 0. I have students who are like, no, you can't do that. You can. 0 times 0 is 0. You're good. You just cannot take the square root of a negative number. Okay, so this example encompasses so many things. First of all, change this radical to the square root of x plus 2 to make it more interesting. First, we'll focus on looking at the denominator. Well, I guess it doesn't matter. You decide. But we first had talked about setting the denominator equal to 0 and solving for x. Okay, so if we're looking for the domain, we want to exclude any values that are going to make the denominator equal to 0. So you're going to set the denominator equal to 0 to find those values. There we go. Set it equal to 0. And we're going to solve. Now, you might use the quadratic formula. I'm going to remind you of what it is, or you can solve by factoring. There are a lot of problems in this first set of notes where we can actually just solve it by factoring. And I tend to do that if I can. It's just easier. Negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So if you find that you'll need the quadratic formula, then you can use that. If it's factorable, then don't worry about it. You can just factor it, which I'm going to do here. So if you don't remember how to factor this, I'll remind you right now. There's a method called the AC method I like to use. I don't care how you factor, just as long as you factor it correctly. I know some students learned to use something called the box method. Okay, fine. If you want to use the box method, be my guest. Some students use guess and check, which I think is similar to the box method. I don't like to guess. I like to know my answers right. So I use the AC method, which means that you're going to multiply A and C. And if you don't remember what A and C are, oh, you know, I just put a bunch of variables here and I didn't give you an example of a quadratic function. AX squared plus BX plus C. That's where A, B, and C come from. So your quadratic function. So in this case, A is 3 and C is -1. So I'm going to take 3 times -1 and get -3. I'm going to look for two numbers that multiply to -3 and add to -2. So for instance, I know that if I take -3 times +1, I can add these two up and I'll get -2. If I switch the negatives, then I would get +2 and that wouldn't work. So these numbers have to add up to give you B. And as long as you get that, then you split this up using factor by grouping. So once you have these two values, you're going to turn this into a 4-term polynomial. Now, it does not matter which terms you stick these with, just pick something. So I'm going to rewrite -2x as -3x plus 1x. And we'll factor this now by grouping. I'm going to take the GCF out of each group of terms. So I'm going to group the first two, and I'm going to group the second two. The GCF out of the first two is 3x. That leaves me with x minus 1. And out of the second two, the GCF is just 1. That's all they have in common. So I must show that I'm taking out the 1. And remember, you should be able to distribute this back in and verify that you get what you started with. Now you're going to look at the whole thing and take out the GCF. The greatest common factor here is x minus 1. And that leaves you with 3x plus 1 equals 0. Remember, factoring by grouping works when you get these two factors to be exactly the same. Otherwise, it does not work. And then you have to try another method, which usually means if you're trying to solve an equation, you can use the quadratic formula. Remember, the quadratic formula works every time on a quadratic equation. Factoring only works sometimes. All right, so now you're going to use the 0 factor property. You're going to take each factor and set it equal to 0. So I'm going to take x minus 1 and set it equal to 0, and 3x plus 1 and set it equal to 0, and I'll solve for those values of x. So in this case, x equals 1, or x equals -1/3, subtract 1, divide by 3, are values that we must exclude from the domain because these are values that end up making the denominator 0. So we're going to put this in interval notation in a minute. Right now I'm going to put a box around them so we can easily find them later. So those are the two values we're looking for. As far as the numerator is concerned, remember we have two different things we're looking out for. We're looking for fractions where the denominator might possibly be equal to 0, and we're looking at radicals where we have an even index on the radical. Remember that if the index isn't written, it's assumed to be 2. So if this is a square root, the square root has an index of 2. Any index that's greater than 2 will be written. The cube root, has a little 3 there. A fourth root will have a little 4 there. But this is a square root, so I need to verify that the quantity under the radical is always going to be positive, or I need to force it to be positive. So what we're going to do is we're going to take the radicand, which is x plus 2, and force it to be greater than or equal to 0, so I can get the values in the domain that x can possibly take on. If x is any value outside of that, then you'll end up getting a situation where we can't define a value for y. So subtract 2 from both sides, and you get x has to be greater than or equal to -2. So this is another restriction on the domain. Now, technically, I know your notes use this notation, and sometimes your homework uses that notation, and other times it asks you for interval notation. I'm going to use interval notation for this one just because there's a lot going on. Now, x has to be greater than or equal to -2. So any value below -2 we can't use. So -2 is actually going to be the first value in the domain. But you're going to look at all 3 of these values, and you're going to pick the smallest one. And you're going to start from there. I know we have to be greater than or equal to this value. So I'm going to start at this value of -2. Now, we can be equal to -2 because the square root of -2 plus 2 is the square root of 0, which is okay. But notice that if I picked anything that was less than -2, like -3, the square root of -3 plus 2 is the square root of -1, and we can't do that. We're going to go up to the next value. So again, you're working your way from left to right, from the smallest value to the largest. X can't be equal to -1/3. So everything's fine from -2 to infinity, except you've got these issues with the denominator. So we need to go ahead and set those aside here. So I'm going to go all the way up to -1/3. And then I'm going to say, all right, we cannot be equal to that value. And then I'm going to use a union symbol and then start back up at -1/3 and then hit the next value that's causing us a problem, which is at 1. Can't be equal to that value, so I'll use the parenthesis. But any value after 1 is fair game. It's totally fine for our domain. So I'm going to take this all the way up to infinity. And this will be the domain for the function in this example. So there's a lot going on in this, but it's just one example that has to illustrate a lot of things. So a lot of concepts were covered in this one example. But again, they are review. Common graphs to know. Oh, this is so important, so important. Now, I can't force you to memorize these graphs. You should have learned them when you were talking about library of functions back in college algebra. I want to say it's like section 3.4, but I can't remember. It's been a while since I've taught college algebra. The first one is the identity function, f of x equals x. Y is just going to take on whatever value x has taken on. It's called the identity function. The next one is your standard parabola, y equals x squared. Whatever value you get for x, y is just going to be the square of that value. So if x is 2, y is 2 squared, which is 4. And it's going to do that the whole time. 1 and 1. You're going to get these key points on each graph. So it's going to be 1, 1, 2, 4, -1, 1, and then, whoops, -2, 4. Oh, we can't forget about 0, 0. Oh, I know why this looks funny, because that's actually -1/2, not -1, 1. I got to get my my whiteout pen up here. Now that I've botched it, I should use a pencil, but pencil kind of glares. This one is your radical function. If you're not sure, note that when x equals 4, y equals 2. So this is your square root function. And you do still have this point at 1, 1. So those are going to be key points in your square root function. The next one is your cubic function, x cubed. You're going to have points at 0, 0, 1, 1, 2, 8, which you can't see, -1, -1. But this is also a pretty important standard function that we should know. You should have done a lot of work in algebra with shifting these graphs around, up, down, left, right, doing reflections, stretches, compressions, all kinds of fun stuff that started out cool and then ended up being really a lot. This is your absolute value function, the absolute value of x. It's V-shaped. It just means that y is always going to take on up whatever x is, but it's always going to be a positive value for x or for y. So x can take on negative values, but the y value that comes out is always going to be positive. And then this one is your reciprocal function, 1 over x. That one students tend to not remember as much, but you'll find that it's really useful in calc, and you're going to see it quite a bit, even especially if you take more calc classes after this. The reciprocal function shows up a lot. There's a lot we can do with it. So that's 1 over x. Oh, it's called the reciprocal function because whatever value y takes on is the reciprocal of x. So if x is 2, well, that's 2 over 1, then y equals a half. If x equals a half, well, the reciprocal of a half is 2. So you get those points. And the reciprocal of 1 is 1. So you always get that point. And the same thing works on the other leg. These are important functions to know. A bit of more algebra review there. Okay, here's where we're going to graph piecewise functions. And I'm not going to do a ton of these. It's not a major emphasis, but it is important that we understand how the graphs work. Again, you should have done it in algebra. We're going to be looking at stuff like this again when we start talking about limits and continuity. So it's really important that we understand how the piecewise function works. Students are always like, are you going to put one of these on our test? I'm not going to put something on your test where I'm just going to say, graph the piecewise function. That's an algebra question. But I might put something on your test saying, discuss the continuity of the function. And you're going to need to know how to graph the piecewise function in order to answer a question like that. Or if I say, find the limit, like, again, you're going to need to know how to graph the piecewise function to do that. So there's more that we're going to do with these, but in order to do more with them, we need to understand the basics of how they work and how to graph them. We already talked about evaluating them. Now we'll talk about how to graph them. What I like to do here is I like to look at the boundary. So remember that you can find the boundary just by looking at these values and the inequalities that are presented in the function. So these are boundaries. I like to put a dashed line through my boundary so I just know where one function cuts off and another one starts. I used to teach piecewise functions by having students graph both functions and then erasing the parts that didn't apply. But I found that after years of doing that, they were still really struggling. So I was like, let's just change it up and start doing it this way. And I feel like this worked a little bit better. If you learned graphing piecewise functions by just graphing both functions and erasing the part that didn't apply, that is absolutely fine with me. I just have to pick one way to teach it, and this is the way that I'm doing it now. So what we're going to do is we're going to just set up a table of values that correspond to just values on these functions. And I need to be able to know which function I'm using when. So I'm going to set up a table for the first function, and I'm going to set up some x values so I can just graph this plotting points. And I'm going to set up the first function, y equals negative 2x plus 5. And I'm going to do something similar for the second function, which is y equals negative square root x plus 4. And if you have alarm bells going off in your head, calm down. It's not a negative under the radical. It's a negative in front of the radical. That's okay. You're taking values, square rooting them, and then making them negative. So this is totally fine. We can do that. All right, so I'm going to pick some values of x that correspond to this function. The only values of x that correspond to this first function in the definition are values of x that are less than or equal to 0. Now, officially, any value that's less than or equal to 0 will be on this graph, but I suggest you always plot the boundary point whenever you can. Even when it doesn't apply, I'll leave an open circle there. So we'll do that in the next one too. Always plot the boundary for both definitions. I'm going to even write that down. Always plot the boundary for both definitions. You know what? I started out my notes today saying, I'm going to have really good handwriting this semester. I'm going to do a good job and make my handwriting really beautiful. And I'm already failing. I'm sorry. I'm going to keep working at it. Keep trying to make my handwriting better. It doesn't help that I'm freezing by this window all the time. And it just makes me like, I'm just cold. I need more blankets, clearly. Okay. I'm going to start out by choosing, I guess I'll start out with x equals 0. I'm going to choose x equals 0 for both. And remember, I know it doesn't apply here to the second definition because we're only looking at greater values, but I'm going to show you what to do with that in a minute. Now I'm going to choose values of x that are less than 0. So maybe -1, -2, -3. I don't have to get too crazy with this because this is a linear function, so I kind of already know the behavior, and it's just a line. So I don't really need a lot of points to graph a line. But let's go ahead and do that. We're going to let x be 0. So -2 times 0 plus 5 is 5. Okay, that will give us 1 point. So 0, 5, and this is the definition where we can be equal to 0. So I'm going to put that on the boundary. This is not an asymptote, by the way. It's just so that I know where one function stops and one starts. It's not an asymptote. Not an asymptote. Oh, I'm still failing with my handwriting. Oh, I need to be better. Maybe it's the pen. Maybe the gel pen is too smooth. So I have a point at 0, 5, and I can put a filled in circle there because this actually belongs on this graph. At -1, I have -2 times -1 plus 5. So that's 2 plus 5 is 7. So I'll have a point at -1, 7, which is right here. And then -2 times -2 plus 5 is 4 plus 5, which is 9. So I have a point at -2, 9. And it's a really good thing now that we decided to stop here because I wouldn't be able to plot any of these other points on this particular grid because my next point would be at 11. You can see that with the slope, it's going to go 5, 7, 9, 11. This is linear, so we can predict the pattern. So we don't need this. We're good. We can just go ahead and connect these with a nice smooth line. We know it's going to just be continuing that behavior as we head up and to the left. Notice that you can check that by the definition of the function. The slope is -2. That means it's going to go down 1, right 1, down 1, right 1 all the time. It is doing that. So everything looks good. For this part of the function, for the other piece, I'm still going to graph the boundary point, but I'm going to make it an open circle since it doesn't technically exist there. But remember that any value that's even a little tiny bit greater than this, not just 1. I know we're going to talk about graphing. We're going to look at 1, but I don't want to just worry about that because I could have a value on this graph that's like 0.001. Technically, that's greater than 0, and it belongs. That's why I like to put the boundary point on because it gives your graph a little bit more continuity and it doesn't just chop it off or stop it at x equals 1. You want to get close to your boundary. So when x equals 0, y equals negative square root 0 plus 4, which is negative square root 4, which is -2. So remember your order of operations, take the square root, then make it negative. So that's a point at 0, -2. Leave this open. It's an open circle because of this greater than sign, just for the boundary. We're going to leave it open. So at 0, -2, I have a point. If I close the circle, my function would fail the vertical line test. If I leave it open, it says that my function doesn't actually exist here. It's just going to guide the direction of the graph. I can't see your faces to see if you're like, yeah, this makes sense, or if you're like, what the heck is happening here with this open circle? So we do what we can. Choose values of x that make sense, that you're actually going to be able to plot and that you can actually evaluate. For instance, I know that I can take the square root of 4, but if I try to let x be 1, you can choose 1 if you want. I know we said we would talk about it. But if I let x be 1, then I'm looking at the square root of 5, which is not the end of the world. We can put that into our calculators and get a decimal approximation for it. But you might want to start out by choosing values you can actually take the square root of. For instance, after 4, I know 9's the next perfect square. If I wanted to get a perfect square, I would need x to be 5. If x was 5, then y would be negative square root 5 plus 4. And the square root of 9 is 3. So that would give me a nice point on this graph, a nice point. So I could put a point here at 5, -3. So 1, 2, 3. And that will be filled in because it actually exists on this graph. It's not part of the boundary that doesn't apply. Now, the next value that would give you a perfect square, well, your next perfect square would be 16. So it would go 4, 9, 16. To get 16, you would need x to be 12. We can eyeball that, but we're going to have to add some points here for x equals 12. So negative square root 12 plus 4. Well, the square root of 16 is 4. So negative 4 would be the y coordinate for that point. So if we went up here and we included a tick mark up to 12, I could go down here to y equals 4 and plot a point there. Now, this is fine with me because you don't actually need to come up with a lot of points in between. If you would like to, you absolutely can, but you're going to be just graphing these decimal values. I mean, let's say, for instance, we chose instead of 5, let's say maybe we wanted to put a point here at 2. We can do that. You would just say y equals negative square root 2 plus 4. And then you'd have negative square root 6. And then you would just have to get that value in your calculator. The square root of 6 is about 2.5 is about as close as you're going to get it to be. So let's say it's approximately 2.5 or negative 2.5, sorry. Negative 2.5. Okay, so we can plot that when x is 2, y is negative 2.5. And I mean, you know, as long as it looks like it's, you know, following the behavior of this graph, we're good. And we're not expecting this to be a straight line because this is a square root function. And the basic square root function looks like this. So we kind of have an idea of what it's going to look like. It starts out a slightly steeper, but then it really just shallows out. It's not a line, but it's a very shallow curve. But this one is being reflected about the x-axis after it's been shifted. So, and by the way, it was shifted and we are not including all those points on our graph because it was shifted to the left 4 units. So the first point would have been over here, right here at negative 4 and 0. But that wasn't part of our definition. So you're only seeing part of this square root function. So it kind of looks like that. Put an arrow on it so you can indicate the behavior that the function continues to move in. All right. Now to the part that everyone, oh, this is it, by the way. This is the complete function. If you want to label the axes, that's probably a good idea, y and x. That's it. That's your piecewise function. It's beautiful. Isn't it beautiful? It's beautiful. All right. Next, applications, which you've all been waiting for. All right, let's end the section with a couple of common function applications. Absolutely, it's a great idea. It's one thing to be given a function and be able to work with it, but it's another to be able to generate your own function for data, which is a very, very powerful tool that you can have as a math student. So let's do that now. A machine initially worth $120,000 depreciates completely, linearly over 10 years. Depreciates completely means that its value goes to 0. Value goes, sorry, it should say value goes to 0. Okay. So this is a machine. I know cars depreciate a lot for the most part, depending on what kind of car it is. But this is a machine. It's going to depreciate completely linearly over 10 years. So we're going to find and interpret the slope. Now, there are 2 ways of doing this. One is just a little bit more of like you using your mathematical reasoning and coming up with a slope, which I'm not going to, I can't really teach you that skill. So the skill that I'm going to teach you is to find the 2 points that are going to dictate your slope. So remember that your slope formula uses the variable m, and you are using y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that is a formula from way back when in algebra, not even college algebra, like algebra intermediate and basic. But you maybe haven't used it in a while, so we'll talk about it now. So it's the change in y over the change in x. So we're going to come up with 2 points. Generally, we let X represent time in a situation like this where we're talking about time, and then Y can represent the monetary value. Let X represent time in years, and then let Y represent the value, and that's in dollars. Okay. So we're going to do that. We're going to come up with 2 points. The first point will be initially how much the machine was worth, given that information. So at 0 years, the machine was worth $120,000. So that's going to be 1 coordinate point. 0 years, 120,000. Anytime you're putting a number with a comma into an ordered pair, be careful. You don't have to include this comma in the number if you don't want to. Don't let it throw you off. Now, after time equals 10 years, it depreciated to $0. So these are your 2 ordered pairs. It does not matter which one you let be X sub 1, Y sub 1. I'm just going to pick the first ordered pair and label it X sub 1, Y sub 1, but it doesn't matter. Either way will work. And then X sub 2, Y sub 2. Just as long as in each ordered pair, you're using the subscripts consistently. This will be subscript 1, and then the next ordered pair will be subscript 2. But you can switch the points. It does not matter. So I'm going to take the difference in Y over the change in X. So Y sub 2, which is 0, I'm looking for the slope here. Y sub 2 minus Y sub 1 divided by X sub 2 minus X sub 1. And you will come up with negative, because this is negative in the numerator. And when you take 120,000 and you divide it by 10, you just lop off one of the zeros, or you can always put this into your calculator. So it had 4 zeros, now it's going to have 3 zeros. So this is the find the slope portion. The next thing you have to do is interpret the slope. Now, a negative slope is representing this depreciation here. It's showing that the value is decreasing over time. So we're going to say that this is the slope itself, but to interpret the slope, we're going to say that this represents $12,000 per year lost in value. Per year drop in value. Now, as long as you're saying that it's a loss or a drop, then you don't put the negative on it. The negative is part of your slope, but it represents that every year your investment, or your machine in this case, is decreasing in value by $12,000. So when we are interpreting this, that negative sign gets replaced with some word that indicates that the value is going down. So that's part A. Part B is express the value V as a function of the age N. Now, one thing that we can think about here is just considering what this would look like if it was a graph. You know, I know you guys aren't always used to thinking about things in terms of graphs. Because I teach math, everything for me is like a graph. I think about everything in terms of graphs. It's a really good habit to get into, I think. Gives you visual representation of your data. If you let X represent the time in years, and I'm going to just do all this in terms of Y and X, and then we'll switch it over to V and N, because it's good to be able to know how to switch those variables. Also, we already called these X and Y in part A, so I'm going to use those for right now. Initially, you bought the car and its value was 120. Oh, I keep calling it a car. It's because my husband has all these friends who have these ridiculously expensive cars. And when I think of a machine that's $120,000, I think of this like Ferrari. I think the Ferrari is more than that, but what do I know? All right, so it started out at 120,000, and by the end of X equals 10 years, it depreciated down to nothing. Okay, so it's just this line. It's got this linear depreciation. I know this line doesn't look exactly straight, but that's what it looks like. Now remember that when you're writing a function, you're using the general form y equals mx plus b, where b is the y-intercept. You would be intercepting the y-axis here at 120,000. So we would say that y equals, well, the slope, which we found in part A, is negative 12,000. And then the x, remember, is your general x. And then plus b, well, b is the y-intercept, which is 120,000. That's it. That's how you write the function. If you were just asked to write this function y and x, you'd be done. However, you were asked to express the value v as a function of the age n. So the age of the car is how many years, the age of the machine is how many years you have since you purchased it. That will be represented in this case. You're going to swap out the x with n. And the v is the value, and we're going to swap out the y for v. So this will be v equals negative 12,000 n plus 120,000. Okay, so you could determine the value of that machine for any number of years until you hit this place where the value zeroes out. So if you were to look at the value at 5 years, you would just say, okay, well let's let n be 5. And you know, if you just wanted to even put that into your calculator and get an approximation, negative 12,000 times 5 plus 120,000 means after 5 years it depreciated to 60,000, which makes sense. It's taking 10 years to depreciate all the way down to nothing. So at half of that time, it would depreciate to half of its value. But that's what the function is doing. It's giving you a general formula so that you could figure out the value of the car at any age. So even if you were like, well, how much did it depreciate after 6 months? Well, the age at that point, I said car again, I've caught it, would be, oh, wow, I don't even know. Oh yeah, never mind. I know what I did there. Insert 0.5. If we were looking at 6 months, then I would be doing 0.5 because that's half of a year. And after 6 months, this machine has already depreciated to $114,000. So it's already lost $6,000 in value in just 6 months. But the function helps so that you can figure out the value of the car at any time in its life, the machine. All right, so we have another application to do, just one more, and then we'll be done. This is going to use the concept of a parabola, and you did applications like this again in algebra. This should not be brand new for you. So the background information that you need for something like this is just that you're talking about the height of a projectile that can be modeled by a second-degree polynomial, which is a quadratic equation. You could have different independent variables, though, that are represented by x. So for instance, you could let y be the height of the projectile, and x could be the horizontal distance the ball has traveled. So you could let x represent that. So like maybe you would say that y is measured in feet and x is measured in feet, and x would be just representing the horizontal distance. So the idea is the projectile goes up into the air, and it's going to hit this maximum value, and then it's going to come back down again. More commonly, x can be a variable that represents time, like we did in the last example. So now in this case, you would still get the same type of function, but it would look a little bit different because this is relating the height of the ball to how long it's been in the air instead of using the x-axis to represent the distance it's traveled. So the path doesn't look like the path of the ball, but you're seeing now that at a certain number of seconds, time in this case is measured in seconds generally because a particle is not going to be in the air. For particles that you're going to be throwing, they're not going to be in the air for that long. So it's usually measured in seconds. So this will show the height of the ball at a given time measured in seconds. And you can get some information then about how long it takes the ball to reach its maximum height and how long it's going to take the ball to hit the ground again. Something like that. Okay, now we're going to set up our own, you're going to be given a function here to relate some data here, and we're going to answer some questions about it. All right, so suppose Fatima threw a basketball from the court towards the hoop and she makes the shot. The function that gives the height in feet at any time t in seconds is h of t equals negative 16t squared plus 20t plus 6. If this looks familiar to you, it's a very standard type of function that you would have seen in an algebra class. It's just your general motion equation for particles that are flying through the air on planet Earth. All right, so from what height was the ball initially released? So we're going to be using this function to answer questions, and a lot of times the question, like you're not going to be told here, find h of this value or find h when t is this value. You're going to have to determine what the question is actually asking you to do. So in this question, you're being asked from what height was the ball initially released? So you're trying to find a value for h. From what height, that's what you need to find height when the ball was initially released. Initially released means like time equals 0. She threw it, and as soon as it left her hand, like time started being counted on the clock. So initially released means t equals 0. And by the way, you know that this function here correlates to something like this situation because you're being told that t represents time in seconds and h represents the height of the ball. So we're going to figure out what the height is when t equals 0. And to do that, we're just going to be evaluating this function at t equals 0. So we're going to say that h of 0 is negative 16 times 0 squared plus 20 times 0 plus 6. And both of these two terms are going to zero out because they're getting multiplied by 0, and that leaves you with 6. And you don't put a box around it and move on yet because 6 is not an answer in an application problem. The question is, from what height was the ball initially released? You were already told that height is being measured in feet. So you're going to say that this is 6 feet. Now you can put a box around it. You were probably also taught years ago, and I think it's a great idea now, to make sure that your answer makes sense. So you should be asking yourself, does it make sense that she released the ball from 6 feet? Of course it does. And if you're like, wow, she's really tall, she's 6 feet tall. I mean, first of all, that wouldn't be that odd. There are 6 feet tall women out there. I don't happen to be one of them. I'm like 5'3½". But 6 feet just represents the height at which the ball is being thrown. So even if she's 5'3½", as long as her arms are reaching up, however many extra inches that would be, 8.5 inches, she's starting the ball from 6 feet up. So it's just determining at what height is the ball initially being thrown from, and that would be 6. So if you are kind of trying to draw a representation of this, that would be a great idea. I would suggest that you make note of the fact that if h is the height and t is the amount of time, the initial height at time equals 0 occurs here when t equals 0, is 6. Now, I don't want this to get super high, but I mean, think about it. She's throwing a basketball. How high do you think it's really going to go? I mean, it's not like I need to scale this out to like 100 feet. No one's going to throw a basketball that high. But maybe I would say that, okay, this is the 6 feet that it's initially being thrown from. And we know that the ball is going to follow this path where it's going to go up and head back down. Now, the ball is somewhere along this path. It's going to be, you know, moving its way through, but you know that no matter what, it starts over here. Now, if you're following this path, it means that officially, mathematically, the graph does exist over here to the left of the h-axis. But we can only talk about this in terms of time. And time only is going to include the positive t-axis. We cannot have negative time. So even though, yes, mathematically, this graph will also swing its way back this direction, in terms of our application, it starts here at t equals 0. Okay. I think that's important to say. If the hoop is 10 feet high, how long was the ball in the air when it went through the hoop? How long means find t. The hoop is 10 feet high. When h equals 10. That's it. The skill here is being able to interpret the wording of the exercise into mathematical language. When h is 10, h represents the height of the ball. Find how long it was in the air if it went through the hoop. Now, we have to also get an understanding of where we think this hoop is. We know it started out at a height of about 6 feet. We know it's going to go up into the air, and it's probably going to have to go back down a little bit before it hits the hoop or the net, whatever you want to call it. Right? This is my very crude representation of the basketball hoop. So we're going to have to figure out when that happened. So let's go ahead and find t when h is 10. We're using this function. I'm going to say that 10 equals negative 16t squared plus 20t plus 6. Now, in order to solve a quadratic equation, I must have one side of the equation set equal to 0. Sometimes students look at a quadratic equation and they're like, I don't remember what to do. They start doing all kinds of weird things. They'll usually subtract 6 from both sides and be like, okay, now what? You have to have your quadratic equation set equal to 0 before you can do anything with it. So let's go ahead and subtract 10 from both sides, and you'll get negative 16t squared plus 20t minus 4 equals 0. Now, if I can solve this by factoring, that's what I'm going to do. So the first thing I'm going to do to this particular equation is I'm going to factor out a negative 4. I don't like my lead coefficient to be negative, and it's negative 16 right now. So I'm going to take the negative 4 out since it's common in all three terms. And that's going to leave me with positive 4t squared minus 5t plus 1 equals 0. Double check this. Make sure if you distribute it back in, you get exactly what you started with. And we do. So we have that. Now we can go ahead and say, well, I can technically, because now I have two factors here on the left. If you divide both sides by negative 4, well, 0 divided by negative 4 is still 0. So we don't have to worry about this negative 4 outside of here because there's no variable on it. If it was negative 4t, yeah, then I would have to use the 0 factor property and also set that factor equal to 0. But there's no variable on it, so we can just divide it out. So what that leaves me with is this equation. 4t squared minus 5t plus 1 equals 0. Now, you can solve this by factoring, because I think we have another one of these to do. Or we can use the quadratic formula. You know what? Maybe I'll do factoring one more time on this, and then for the next one we have to do, I'll do the quadratic formula. I just like factoring. It's just easier, I think. Fewer places where you can make a mistake. I'm going to use the AC method. I'm going to multiply A times C. So I'm going to multiply 4 times 1 to get 4. And then I'm looking for two numbers that multiply to positive 4 and add to negative 5. And those two numbers will be negative 4 and negative 1. If I add these together, I get negative 5, which is exactly what I want. So now I'm going to rewrite the negative 5t as negative 4t minus 1t. And again, the order of these two doesn't matter. I like to keep the coefficients together, but it does not matter. So minus 4t minus t plus 1 equals 0. And then I'm going to factor by grouping. I'm going to look at the first two terms, then I'm going to look at the second two terms. So for the first two terms, I'm going to take out the GCF of 4t, and that leaves me with t minus 1. And for the second two terms, they only have a 1 in common, but if the third term is negative, you should always take out the negative GCF, always. So take out a negative 1. And that leaves you again with t minus 1, because negative 1 times negative 1 is positive 1. And remember, these have to match. So if you don't take out the negative, they won't match. All right, now you can take out that GCF of t minus 1, and that leaves you with 4t minus 1 equals 0. Now you can use the zero factor property, because now you've got a case where you've got two different factors that are equal to 0. So either we have t minus 1 equals 0, which means t equals 1, or 4t minus 1 equals 0, which means 4t is 1, which means t is 1/4. Now, back in algebra, when you solve these, a lot of times you ended up in a situation where one of your t's was negative and one of your t's was positive. So you knew you had to keep the positive because t represents time, and time can't be negative. But in this case, you're like, gosh, I don't know. Which one's the answer? Well, this is why it's really helpful to write a diagram. We drew this out, and we had a really good idea of what was going to happen. Notice that if your basketball hoop is 10 feet high, the ball actually is going to hit this value twice. So when she throws the ball into the air, it's going to hit 10 feet at t equals 1/4 seconds, so 0.25 seconds. And then it's going to go up, it's going to hit its maximum height, and it's going to come down again. And when it does that, and it goes through the hoop, that's happening when t equals 1. So you're going to have to figure out which t it must be, and it must be t equals 1. So if you want to complete this, technically you'll say t equals 1 second. This is your answer. This one is, I don't want to say like X it out, because it's not like it's not an answer. It is an answer, but it's not an answer to this particular question. So we can say we don't need that here because that represents this quantity. If you're like, well, how do I know that? What if we just drew the diagram wrong? Well, I mean, how else could it happen? Because you're not going to have the ball go through the hoop. I mean, it would have to go through the hoop from the bottom in order for you to have it be at t equals 1/4. I mean, she'd have to throw it up, and it would have to go through the hoop from the bottom and then go back up again. And that can't be. It just doesn't make any sense. So it's definitely the second time it hits that value. It's going to go through and then it's going to head back down. Okay. That is A and B. The other questions we have to answer are C, when does the ball reach its maximum height? Let's see, I'm going to write this function down because we're going to use it, and I have it on the previous page. Negative 16t squared plus 20t plus 6. Okay, when means find t, when denotes time, does the ball reach its maximum height? So we need to figure out when we're actually hitting this value. Now, because we just did this question, there are actually two different ways of doing this. I'm going to show you the general way. If you're like, well, it's 10 feet at 1/4 second and 1 second, so it's got to be in between those two, that's fine. Take the average of 1/4 and 1, and you will get the time in which it reaches its maximum height. It's got to be smack in between those two values when it was at 10 feet. But you might not always have that already done. So we're going to have to figure out, find t at the vertex. So the vertex is where it's going to reach its maximum or minimum. And in this case, it's a maximum value at which you hit that turning point of the parabola. If you don't remember the equation for finding the x-coordinate of the vertex, well, I'm going to remind you, the vertex of the parabola is at negative b over 2a, and then the y value is f of negative b over 2a. We just need to find t at the vertex. T in this case represents the x-coordinate because we're letting the x-axis be represented by the variable t. So we're going to find t at the vertex, which means we need negative b over 2a. And instead of saying x equals negative b over 2a, we'll say let's let t equal negative b over 2a. And that'll represent the time. Now, the height, the maximum height, will be represented by the y-coordinate of the vertex. But in this case, we're just going to find the time, which is represented by the x-coordinate of the vertex. So this is negative b, which is negative 20. Remember, b is your linear coefficient, divided by 2 times a. A is your quadratic coefficient. And then we'll simplify. It's a negative divided by a negative, so it's going to be a positive. 2 times 16 is 32, so you'll have 20 over 32. Simplify that, and since it's an application, we'll probably want this to be either a decimal or some value that we can clarify to make it look a little bit simpler for us. Probably not. I mean, it can't be an improper fraction anyway at this point. But I know 4 goes into both of these. So I can simplify and get 5/8. So 5/8 as a decimal is 0.625, and it's exact. So as long as it's exact, you can leave it as a decimal. And since it's time, you might want to write it as a decimal versus writing it as a fraction. Just because we don't talk about time in terms of fractions. Again, if my son asks me what time it is and it's 7:30, I don't tell him it's 7 1/2. I mean, I could. I think he'd know that, but it's just a weird thing to say. I actually don't tell him it's 7.5 either. But if he asks me how many more minutes till we leave, I'm not going to tell him 5/8 minutes. I would tell him like, I don't know. Now I'm trying to make this practical and it's not working. But you know what I'm talking about. We'll measure time in seconds and we'll call it a decimal if it makes sense. If it's exact. Otherwise, I'll give you rounding instructions. What was the maximum height? So if you know that it reaches its maximum height in this amount of time, we'll just figure out then what the height must be at that time. And that really corresponds to what's happening here. It's the function value at the vertex. In this case, our function is h, not f. No big deal though. So we're going to find h of, let's just say 5/8 in this case. And then we'll put this in our calculator and I'll show you, if you don't know, how to leave your answer as a fraction, and then we can simplify it as a decimal. But actually, this will give you a really nice decimal value. So if you wanted to find h of 0.625, that's fine too. You should get the same thing. In my calculator, I am getting 12.25 feet. And it's feet because we're talking about the maximum height. Okay, so that's maximum height. And again, it should make sense if you draw out a nice diagram. Your t value is 5/8, which you will find is the exact middle of 1/4 and 1. If you were to take the average of those two, you'd get 5/8, which is exactly where this maximum occurs. And if you know that it has to be higher than 10, you know it can't be that much higher than 10. The value of 12.25 makes complete sense here looking at the diagram. So we can do that. I'm going to actually show you how to do this in your calculator in case you haven't done this in a while. You're going to find it's a really helpful tool to have at your disposal. I'm going to put this function in. You have to write it in terms of x in your calculator. It doesn't know what to do with t. It's programmed to use functions for x. 20x plus 6. Negative 16x squared plus 20x plus 6. I'm going to zoom standard here. I know that I'm not going to get the max to show up because the max I know is occurring at 12 point something, but it gives you a starting point. If you know that you're only going to be using positive values of t, set your minimum x value to be 0. And we know that the vertex is occurring at about 5/8. So that's the midpoint. So this is not going to be in the air that long. We're going to find out when I hit the ground next, and I'll show you how to do that, and then we'll verify it. But I mean, maybe go out to 2 seconds. It's going to be hitting the ground before then. And then the y-min, we're not talking about the ball going underground. And then maybe just set the max to 15 so you can get a good picture if you already know it's going up to 12. Otherwise, you're just going to have to play with these numbers in your window until you get something that looks good. All right, so there's the 6 feet it started at. The maximum value is occurring right here. So the way you would do this is you would go into second calculate, and then you would hit number 4 for maximum, and it's going to ask you for a left bound. You're just going to scroll over so that you're to the left of this maximum value somewhere. I mean, just eyeball it, and then it's going to ask you for a right bound. Sorry, so I hit enter, and then it asks me for a right bound. So I'll do this, and then I'll hit enter again. And then it's going to say guess, and I'm like, yeah, please do that. And it's guessing that your maximum is at a value of 12.25 at approximately x equals 0.62499, which is your calculator's way of getting super close to the actual value. It's only going to be able to get so close, but it should match up with what you found. Your exact value will be better than your calculator's, trying to extrapolate and approximate. Now, the next question we're going to ask, the last question we have is, if the basketball hoop was not there, how long would it be until the ball hit the ground? So what you'd be asking yourself there is find the value of t when the ball hits the ground. So, of course, once it intercepted the basketball hoop, that sort of like changed its trajectory. It's going to kind of go through, and then it's going to lose its momentum and head downward. But if the basketball hoop wasn't there, the question is, how long would it be until it hit the ground? So we'd be looking for how long is a t-value when the height would become 0. So when it hits the ground, the height is 0. So find t, the time, when the height is 0. Now, if you'll remember, though, from our diagram, I'll remind you, the height is also going to be 0 over here. So when you solve this equation, you're actually going to get 2 different values of t. I'm going to show you how to find one of them in your calculator. We only need the one that really corresponds to our answer. And then we'll solve a quadratic equation to actually find that value. So back to your calculator. I believe to find a 0, it needs a little bit of space underneath the axis. So I'm going to go back to my window. And I'm going to set my y-min to -1 just to give it a little bit of space underneath the x-axis. All right, so it's going to graph that again. So we want to know after how long does it hit the ground? And we can do that by going to second calculate and then finding the 0 value, which is number 2. Finding a 0 is finding an x-intercept. So I'm going to go to the left of the x-intercept, and then I'm going to go to the right of it. So the left gets me like right here, hit enter, get to the other side of the x-axis, and then hit enter again. And yes, enter will have it guess, and it's going to tell you the 0 happens at 1.5 exactly. So when x equals 1.5, y equals 0, or the height is 0. So from our calculator, we get that t must be 1.5 seconds. I'm going to show you how to use the quadratic formula. It's been a while, so we're going to verify that with the quadratic formula right now. Remember that the quadratic formula I wrote down for you earlier is -b plus or minus the square root of b squared minus 4ac all over 2a. I'm going to write it down here again, I think. -b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to fill this in. So -b, I have your function up here is -20 plus or minus the square root of b squared, so that's 20 squared, minus 4 times a, which is -16, times c, which is 6, all divided by 2a. The reason I think the quadratic formula can be harder for students is because of the simplifying. They know how to do this, but simplifying it somehow gets really messed up. Okay, so I'm going to work under the radical first. So I have 20 squared minus a negative is plus, but you can always just enter it this way. Minus -16 times 6. Oh, I forgot my 4. Yikes. Insert my 4. 20 squared minus 4 times -16 times 6. So this is -20 plus or minus the square root of 784 divided by -32 we already said that a negative 20 over negative 32 is 5/8. If you're like, wait, why? That's weird. We are seeing it again. Yeah. That's because the x-coordinate of the vertex is just part of your quadratic formula, negative b over 2a. See that? That's why we're going to see this 5/8 all over again that we got here when we did 20 over 32. Same thing. Oh, it's so exciting. 5 over 8. But, oh, actually, you know what? I just did something I keep telling everybody not to do all the time. We're going to have to simplify this first before simplify the radical, because I cannot cancel out in this term unless I split off the fraction first, and I'm not ready to do so. But what I can do, let's just, you know what? We're just going to get a decimal approximation. We don't need to go through all the algebra of simplifying this, actually. We don't need to. I'm so used to just simplifying everything to death. Okay, so negative 20 plus the square root of 784. If you are going to do this all in one action, put parentheses around your entire numerator and then divide it by negative 32. Now, if you're like, how did she know to use plus instead of minus? I'm just showing you both of them so you can figure out which one you're going to use. So there's the plus version. Negative 0.25, we don't want that. So let's use the minus version. I'm going to recall it, switch it to the minus version, and you'll get 1.5. T equals negative 1/4, or T equals 1.5. Remember that to switch a decimal to a fraction, I know we all know this one, but you hit the math button, and then you hit enter twice, and it'll turn any decimal that you have into a fraction, which in this case is 3/2. But again, we're talking about time, so we like to have time written as a decimal. This is the time at which the ball would have been on the ground if time was negative. It doesn't correspond to our application problem, but it corresponds to that function value where t would be negative 1/4 right here. But our time corresponds to 1.5. Make sure it makes sense. It is greater than 1. 1 was how many seconds it took for the ball to hit the basketball hoop. So it would have gone through that. That was at h equals 10. So it has to be greater than that to head off towards the ground. So we can say here that t equals 1.5 seconds. All right. Next time we will talk about 2.2, the algebra of functions. That's all I have for you for 2.1. I hope that you've enjoyed this thoroughly. Exciting stuff. And I gotta figure out how to stop my recording. Okay, bye.